Ready.
Okay, now's the third part that we need to deal with on experiment number 5. Because when the reaction started happening, there was never an instantaneous time when all of the sodium hydroxide and all the HCl molecules bumped into each other at one instant. There was never a time when all of the heat was contained in that 60 milliliters of solution inside our calorimeter. So what we've got to do is graphically try to backtrack and figure out what that maximum temperature would have been had it all been in the solution at a given time. An example or an analogy for that would be if I took a funnel and put my finger over the end of it and poured water into the funnel. Well, right now all the water is in there at one time. That would be what would happen if all the molecules bumped into each other at the same time and instantaneously made all the heat that was going to happen. But that's not the case. What really happened was my finger wasn't over the bottom, and so as I was pouring water into the funnel, it's coming out the bottom a little bit slower than what I'm pouring it in. That would be analogous to some of the molecules have not yet collided and generated the heat, while some of the heat has already left the solution, transferred to the surroundings. So we're going to graphically backtrack and try to determine this number T final from our graph. It is the temperature that we think could have been reached had all the molecules simultaneously released their energy from their bonds. So what's happened is on the x-axis, the times are all recorded in the 15-second intervals. Make sure you use the graph paper in the back of your lab manual or some with the same kind of precision. And notice the axis started at minus 15 seconds. Not that we're going to be using those. That gives us a little bit of playroom on this side. And then on the y-axis are our temperatures. And you don't have to start at 0. Start at your lowest temperature. For example, our data that we recorded today, the lowest temperature we saw was 20.95. So if we started off at 20 degrees here, the way this experimenter did, and then get as big as we can on that y-axis. So here is the time, at time 0, here was our initial temperature. That was that temperature we got when we averaged out the temperatures of the acid and the base before we mixed. And then what happened, just like our data shows, there was a jump in temperature as the reaction started occurring, and on the way up, the first 15-second interval, here was the temperature. Then here was the second 15-second interval, and then the cooling curve started and the temperature started coming down. So this temperature is what we call the Tmax, the maximum observed temperature. The temperature we're trying to seek, T final, to use in our calculations is going to have to be bigger than T max. So how do we get this T final point? Well, what you have to do, just like it says in your lab manual, find the 60% rise point. So take your initial temperature and the T max you observed, take that difference, just like it says here on the graph. Take 60% of it and then add that on to the T initial. So this is not the temperature we're seeking, that is the 60% temperature. So we're going to go back to our graph, and on this line that connects your T initial to the first interval temperature and then curves around and then starts the cooling curve. On this straight line that joins this point to this first one, you're going to find your T max, your 60% temperature on that line. For this person, it's right there. Once you find that on this line, you're going to drop a perpendicular that goes all the way down to this axis and all the way up there. So that's going to generate this line here. Then where this line intersects this one, this perpendicular we just dropped, that's going to be our T final. So how do we get this line over here? Well, it's the line of best fit for these data points, except it's got to go through your T max, and hit as many points on the cooling curve as it can. It's not going to be able to hit a whole lot of them, depending upon what your cooling curve looks like. But make sure that you average them out, giving equal weight below the line of best fit to equal weight above. If you have 5 points below, give me 5 points above to get that line of best fit. So you've got that clear straight edge in the front of your lab manual to use to draw these lines. So this line of best fit that goes through Tmax observed, extrapolate it back to where it hits that 60% line, and that temperature right there is your T final. So you're going to use that temperature and your initial temperature to calculate your delta T. So delta T is going to equal to T final from the graph minus T initial that you recorded. And again, we're using this temperature T final rather than the maximum temperature observed because it gives us a better idea of how much heat we actually generated. It couldn't be directly measured because it was starting to leave the solution. At the same time, it's still creating new heat. All right, so we're going to use this calculation to get our T final. So you've got your data. To help you make this graph, you're going to need 2 pieces of graph paper. You're going to have to make one graph for trial 1, then one very similar to that for trial 2. And then on your data sheet, go back to your instructions, figure out what the total volume of the reaction mixture was, the change in temperature from your graph, that delta T is, remember, T initial minus T final, not T max. Then you're going to calculate using the mass of your solution, its specific heat, and make sure that you use 4.184 joules per gram degree Celsius for the specific heat of your solution because it's almost water. To calculate the joules absorbed by the reaction mixture, then the joules evolved by the neutralization, then the molarity of the acid, that was on the bottles, it's in your instructions, the volume of the acid in the solution, the moles of acid reacted, the moles of water formed by the reaction, and then the molar heat of neutralization. It's in units of joules or kilojoules per mole. So you're going to find out how many kilojoules you generated versus how many moles of not acid, but how many moles of water that were created using your volume and your molarities. And then that's your molar heat of neutralization. You'll do the same thing for trial 2. You'll average those and report them as your average molar heat of neutralization. And so that's when we'll calculate your percent errors. If you will go back to the sample problem that I did for you on the board the Friday before we took our exam, or if you'll go back to your textbook back in chapter number 5, those 2 problems dealing with calorimetry I told you to do before you tried to do the pre-lab. You shouldn't have any troubles making these calculations. I encourage you, if you are struggling, to calculate your contact your lab instructor or myself and be prepared to show us your data sheet so we can kind of see what you're doing. Make sure you're showing us your calculations for both trials so we can track them. So what you're going to do is you're going to upload your pre-lab for experiment 5 before you do this lab. You're going to watch the videos. Remember, there's 3 parts: trial 1 data, trial 2 data, and these instructions that we're now doing to help you with the calculations. Make your calculations and then upload this page 31 when it's complete back into Blackboard for your lab instructor to grade. And then we're going to get a mechanism in place where we'll send you electronically your experiment 5 post-lab quiz and give you X amount of time in order to complete it, and then scan it back in and upload it back to us to grade your post-lab quiz. So that's hopefully how we're going to handle experiment number 5. You can let me know via email of challenges you're having or things that you didn't quite understand. Okay? Let me know when you need my help.